Okay, so what I want to talk about today is I want us to think a little bit about how we would store text. So we were considering, if you had 40 students in a class and you wanted to give each one a unique identifier, then you would need, we said, 5 bits?
Yeah. 6.
Was it 5 or 6?
32.
Yeah, I knew I would get it wrong. It didn't matter. It didn't matter what I went for. So, so how might you do text? That's the question we're gonna look at today. So how many bits do you need to represent a character?
Depends on many characters.
Well, exactly. It depends on many characters.
If you're talking Unicode, you need 8 bits of character.
Well, you see, Unicode is even more than 8 bits. Unicode is 2 bytes. Yeah. So let's pretend we don't know all these things already, and go back to first principles. So for English, for a start, okay, scenario, right? Like Jericho or Walking Dead, like this is our compound. We've managed to secure the perimeter, and the zombie hordes, whatever, are outside, and we're going to try and communicate with UCC or something. There's another compound down there, right? Unicode my arse, right? We're going to devise a small character set, right, in order to transmit messages between here and there. And we won't be using Om or Klingon or Kanji or anything, right? So, I mean, there's 26 letters, we know that much, right? Let's say we're fussy and we're going to go uppercase and lowercase. So we have 26 plus 26. We'd probably want numbers. There's 10 digits. And we'll throw in a few, funky characters for punctuation and whatnot. So we said 30 of those, talking maybe 92. It's interesting actually to look at, and I may even do it if I get organized, but what are the odds of that? But to look at systems, I mean, when we're talking in this module about storing data, we're really talking about, storing it and putting it on a disk. But it's much easier to visualize that scenario where you'd like a transmitter and a receiver and you're trying to send a message. It's just easier to visualize. And it's interesting to look at some of the systems that we've had historically for that. So like we will see in Morse code some of the principles that are applied in modern algorithms. And just thinking there in terms of semaphore, where you have a guy in a bunch of flags and waving his arms on the ship. I think for numbers, if I'm not mistaken, I should have, whatever, next time around. This module will be great next time around. I should have, if I'm not mistaken, for numbers, just kind of like what we would consider now with our 2013 computer science brains, an escape character. You escape for numbers. Because like, in fairness, with only 2 arms and so many positions, it's kind of limited. So to do numbers, there's what we would consider an escape sequence for numbers. God, I hope that's right. If I'm not mistaken, I'll look that up. Not now, though. So 92 characters, anyway, should probably be enough. So how many bits would we need for that? 7. Oh, I thought it would be less. 7's not very impressive. If you wanted to, what could you do with 6?
64.
So you could do so if you really were...
Leave out the punctuation.
Leave out the punctuation, I think, and what would you get then? 20. Yeah, if you left out the punctuation, if you were in a, apocalyptic scenario, I think in an apocalypse, we'd try and make do with 6 bits. 7, I think, would be, you'd be like H-E-L.
With 6 bits, you could still have a space and a full stop.
Yeah. So when the apocalypse comes, we'll throw for a 6-bit system. Okay. No. So we could say something like this with 7 bits. And so here we have a table, right, where you're specifying what the bits mean. Without the table, you've got nothing. You've got a bunch of bits flying around. So the meaning of the bits, as we saw, is assigned somewhere else. And of course, this would be the basis as well for a great code. You can, you know, someone else someone looking at the message just see bits going, and if only you and the receiver have the table, so to speak, the key, then only you can read the message. Now, as it turns out, it's way bottom of the level in terms of encryption, because of course it turns out that in English some things are, you know, you can work from the frequency of the characters and work backwards, and you know, this wouldn't last, you know, 10 seconds in a modern scenario. But if we were in ancient Rome, you know, this would have been good. So we could say something then, we'd see something like the way you read the table then, but I'm sure you're familiar with this. Where's my cursor gone? You'd see, so he points at the screen as if that's going to help you. So you can see with this that something like, here we're going down the left here. Sometimes you start across the top and then work down the side. It doesn't mean, you know, you'd want to establish that if you're reading a table. But here, uppercase C then is like 0, 0, 1, 1, and then up top there, 1, 0, 0. So something like that. Now I made that up, but you'd have something like that. Now, so in order then to decode the sequence of bits, the table that maps them to the characters has to be available, and without that you got nothing, like we said. So some standards were devised. So the most famous or most commonly adopted standard is the American Standard Code for Information Interchange. It's hard to imagine in our 2013 view of the world that there was a time when you would have had computer systems made by manufacturer X that spent their whole lives not talking to other computer systems. So you had a payroll system in a big company, it was in a room, and it did its thing. And to be honest, it didn't really matter what mapping of bits to characters it had, as long as everybody knew what it was. You know, you put in Colin Manning's name, it went in as bits, and when it needed to, those bits came out again as Colin Manning. And everything was fine. When it became necessary or desirable to have different manufacturers' systems communicate with each other for some reason, so let's say I have a file here, you know, on a tape or whatever it was, and I want to read that on another system from a different manufacturer. Well, rather than have to write code that would translate from that table of characters to this other table, we could have a standard. And so that's where the American Standard Code for Information Interchange came from. IBM, which was kind of bigger than everyone else at the time, had a different system called ASCII. And for many years, you know, one of the first programming assignments you did in college was a translator from ASCII to ASCII, and from ASCII back to ASCII. You don't see ASCII anymore, although I'm sure there's stuff still out there in ASCII, but it's probably, the physical media it's on is probably decaying at this stage. But you know, when the apocalypse comes, we may need to, you know, construct as much of our civilization as possible, and there may be stuff on those tapes in ASCII that we need to get at some stage. It is actually a big issue for librarians, you know, that we have stuff in digital form. Like a book has, okay, it has a limited lifespan, physically, the physical medium, and we see that in libraries now books are decaying, and there's a move on to try and scan them as quickly as possible. Sometimes, like, as the page is turned to scan it, that's the last time that page ever gets turned. It just decays. And we think, isn't it wonderful that we'll have stuff in digital form? But of course digital form stuff decays as well. I mean, the files that I wrote, the word processor that I wrote my thesis in for my master's, those original files, I can't open those anymore. So as more and more of our civilization is in digital form, it too can expire. I mean,
It's way harder to recover as well.
it is. I mean, graduation videos on VHS. I mean, what am I going to do with those? So that's why standards are important. Well, it's one of the reasons why standards are important. But just even to, I mean, you may come across a file, say an image file, that's pre-JPEG, pre-90s, and depending on the manufacturer, they may be in a different format. So hopefully you can find somewhere the actual description of that file structure and how those bits make an image. And hopefully there was some logic to it, and you may be able to do that. If not, all you got is a bunch of bits. That could be anything. That could be a shopping list, could be a movie, could be a picture, could be a thesis, who knows. No, so mindful of that, we are creating when we create new structures, we try to create them in a way that makes them as adaptable and as sort of self-declaring and stuff as possible. But it would be fun to, it would be interesting to see something in ASCII and just kind of translate it and decipher it. If I'm not mistaken, a lot of science went into IBM's mapping of the bits, because it turned out that if you have a physical tape, that when you write over tape, and we write over it again and write over it again and stuff, some bits change more often than others, and some bits are more fragile than others. And so they organize their tape, for example, in such a way that it would last longer, because the stuff that was being used less was at the edges and things like that. And, so there's a lot of thought went into some of it. But so we have, what we're left with today is the American Standard Code for Information Interchange, or ASCII. Now, as we'll see, I mean, ASCII had some issues with it. So ASCII uses 1 byte per each character. As it turns out, it only uses 7 bits. 1 is spare. But like we were saying when we were talking about memory and stuff yesterday, like if you have a bunch of bits all organized into bytes, okay, you could save loads of space by using, for the first character, the 7 bits of the first byte, and then for the next character, the last bit of that first byte, and then the first 6 bits of the second byte. But you'd be saying, for feck's sake, like, I'll pay for them, rather than write that code. So it can depend. Now, when it comes to transmitting a message, over a distance, and the cost of transmission becomes higher than the hassle, which is the case in compression, then we start doing things like that. So you can see, for example, if you were compressing text and it was in pure ASCII, well, you wouldn't waste that 1 bit. You would send a sequence, you would basically just send a series of bits, and they would be like 7 bits. The characters would be 7 bits long. So ASCII then has been extended in non-standard ways. So kind of the bottom half of the ASCII table was all sorted, and then there was a bit of a free-for-all at the top, because ASCII was, well, let's have a look. Here's one I made earlier, as they say in the cookery shows. So this is your kind of bog standard ASCII table. To see if we can. Well, no need to make that any bigger anyway. So your space, for example, is 0, 1, 0, and then 0, 0, 0, 0. And of course, we all know as card-carrying nerds that space is 32. So that sounds right, doesn't it? Yeah.
What do you mean it's 32?
It's ASCII 32.
Oh, number 32.
Yeah, number 32.
Okay.
And uppercase A is 65 or 64? 65. So this would be 64 plus 1. So we're looking at 1, 0, 0. So on this table, you see it starts up the top. So we read them 1, 0, 0, and then we should be looking at 0, 0, 0, 1. And so this is the ASCII table. You'd spot the EBCDIC one because there's gaps. They kind of, the letters go in chunks, and there's gaps between them then. There were many things to do with the kinds of things computers did when ASCII was devised. So that's the things at the bottom of the table. So, you know, who knows what some of them are. I mean, you know, there's probably, you know, and synchronize and whatever, and, you know, I don't know. It's all, you know, all Mad Men era stuff. So I'm sure machines had to do some things that wouldn't make any sense. Oh, Bell, it was 7, isn't it? I remember that, yeah. If you output ASCII 7, it goes like a ping. It's be great fun. You'd be outputting text to the screen, but you get a ding. Yeah, and I'm sure it was an actual bell, like in its day.
You can still do that.
You can still do that, yeah. Yeah, you know. So ASCII 7.
You just put ASCII 7 on like in like a print statement or something.
I'd say if you put, even if in HTML even.
Yeah, if you do document.write.
You could do document.write ASCII 7, and the computer might go ding or something. Who knows?
I'll try that.
Be fun to try. I mean, one of these might even be the, oh my God, the Russians are coming self-destruct. Who knows? So some of them are probably not in use anymore. Now, so, si quieres escribir algo en español, ¿qué vas a hacer? There's no N there with a squiggle. You can't write español. If you want to do something in French or in Portuguese, there's some lovely squiggles in Portuguese.
The Americans for you anyway.
Yeah, so for the English-speaking world, that was fine. What about the rest of the world? So what happened then was they were, well, sure, we're using 8 bits anyway, so we'll just fill in the rest ourselves. So then you ended up with sort of French ASCII and Portuguese ASCII, and sort of, well, French ASCII and Canadian French ASCII, and so you see that sometimes today in maybe when you send a text message. So if you you know, if you send a text message in French or Spanish or something from your phone, it might not make it through the network intact. So sometimes if you get a message from abroad, typically what happens, like if someone is using an squiggly an ñ, it's in Spanish, we'd call it N tilde, but it's the squiggle over the N. That's considered a separate character. If people are sending that around Spain, it generally works fine because the Spanish network is expecting that. But if someone sends it to Ireland, it just comes through as a garbled character.
Decodes the message.
It's very complicated, actually.
Because like the phone, like most phones would have different languages on them.
Yeah,
So they have different ASCII ones probably built into the phone.
Well, the newer ones that
yeah. It's actually more complicated than that, because what happens is it turns out that what some of them do is if there's a non-7-bit ASCII character in it, it immediately goes to 2 bytes in some cases. So sometimes if you send a text message in Irish, it can trigger the 2-byte system instead of the 1 byte and things like that.
O2 web text, where it actually tells you
Yeah.
that it's going to be 2 bytes.
Yeah, yeah. But actually, see, if they were to do it right, no, I'm not convinced of this. I believe it. No, I am convinced of it. I'm just not sure it's right. Very, very different. You should be wary of lecturers. It's an occupational hazard to speak with conviction about things of which you're not entirely sure. And I think actually that the network is well capable of handling 1 byte character sets with fathers in them. You just have to set it up right. It's rather like it's kind of lazy to say, "Oh, jizz, we're screwed. Let's go to the 2 byte." You know, like I'm quite sure that when people are sending messages around France, they're not taking 2 bytes per character. You know, so you could use that for Irish. No, if you're getting into Japanese and Klingon, okay, you're in 2 byte land.
So what you're actually saying that it'll actually change everything to 2 bytes?
It changes everything to 2 bytes, not just the character that it changes the whole message to 2 bytes. Yeah, so everything is double the size. So you think, okay, I might have to pay a bit extra for that ifada. No, you pay twice for every character because that ifada triggers the, oh my god, this isn't bog standard ASCII panic attack.
The whole
So
system is kind of a joke nowadays. I mean, it's only 160 bytes. Like,
yeah, but you see, the text messages were never meant for...
yeah, it's actually an auxiliary control.
It was never meant for sending messages. It was just kind of if we would consider it like an operating system feature to allow codes to be sent. Do you know what I mean?
Yeah.
And then figure you could actually send a message using that. I remember in the pub telling people about this, and really, you can send a message? I was like, wow! And we were sending messages. They're like, oh my god, that's amazing. You know, which seems quaint now, but it was amazing. You know, but it was never meant as a communication system for people. It was just meant, you know, for a way to say send a message to a phone. You know, for the network to send a code to the phone to do something, whatever. You know, so things like that.
What's funny though is that it's all digital anyway. So it's really just a keyboard.
Well, the packets are designed in certain ways and things and blah blah blah. You know, networking people know about these things. Now, so this is bog standard ASCII, and we see that it's seven characters long. Just an interesting one. The reason I have pound and pound here is that Americans call this hash here on the right, they call that the pound sign. So sometimes if you phone up a voicemail system, it says, please press pound. And you're like, there's no pound on my keypad. There's only a hash. It's because that's that there. Okay? I remember when I was in college. Oh yeah, the piece of trivia is that they had the same ASCII value. Actually, was that on the table there? Does it show up? Sorry, no. And he closed it. Genius. Okay. They have the same ASCII value in some systems. When I was at college, there were terminals, dumb terminals, and there was a physical switch at the back. And if you flipped the switch one way, all of the pounds would turn to hash signs. And if you switch it the other way, they'd go back to pound signs. Because I guess, you know, depending where you were, you needed to be one way or the other. It was amazing. So
in standard tables, though, would there be the actual hash or the pound sign?
I don't know.
And then when the euro came out, they had to add that in then as well.
You see, the euro then had to come in a different way, and you know, so we had different stats. Where's the hash sign?
Yeah,
It's more than ASCII, does it?
hash the 2 there.
Where's the hash there?
2, 3. Right there.
Sorry, no, I can't see it.
Your mouse on.
Oh, okay, so it's hash there. Okay, and there's no pound there. So there's some issues with ASCII, and so they're all different character sets now and things. And so if you're writing a document in Irish, for example, there's probably a specific code for Irish, but you could probably get away with just using the French one. It wouldn't cost much more. It wouldn't cost any more, and it might be actually more interoperable. So even if it's ASCII, if it's using the top half of the table, you need to kind of say which ASCII. And the main, like saying, the main time we see that is when you're sending text messages around the EU, and if there's accents and things when they leave their home country, sometimes things happen. That's not interesting anymore. But then what about, formatting? And it becomes an issue. So let's say we were going to use, let's say we settled on 7 bits per character, right? That's all fine. But then what happens if we want different fonts? Let's say we could allow 16 fonts and use 4 bits for that. Let's say we weren't pushing the boat out too far and we allowed just 16 colors. Well, then we could have another 4 bits for that. So now instead of 7 bits per character, we're 7 plus 4 plus 4. And then we want different sizes. Okay, if we had 16 sizes, another 4 bits per character, you could see okay, so we've only got 16 colors, 16 sizes, 16 fonts, and I already know the file size is just bananas. So as a way of doing things, that's not going to work. And so that's where we end up then with tags, which of course you're familiar with. So with a tag, we have some kind of an escape sequence where we're saying, okay, this bit here, you have a special sequence of characters that says what comes after me isn't content, it's information about the content that tells you, the receiver, to do something.
It's in binary as well. Escape sequence in binary.
Well, actually, in ASCII, there's probably an actual even character escape for whatever, So we see this in HTML as a tag where you have the open bracket, and that says then, well, actually this isn't content now, this is information about the content, and we have the structure of the tags in HTML. So we see it there. But I want you to think of it more generally as an escape sequence. And like I said, I think in semaphore, if we have time I'll Google it, I think in semaphore, when you want to do a number, there's because there aren't enough arms and positions of arms, there's a special sort of, number thing. You say, okay, what's coming next is a number. So then the next positions of your arms isn't the regular letter one, it's interpreted as a number.
So it's just you don't have to use it if you want that. It's when you put the ball off there,
Yeah.
they're just saying just something extra about it. But it would, you don't have to put that into it every hello. To get right. If you had 20 hellos, it'd be better just do that way instead of having the extra information in all of them, even if you don't use it.
What I'm saying is that if you were to embed the styling, if you were to have the information about the color and the font as part of each character, it would take up so many bits that your file size would be ridiculous. So what you do is you just have a default setting, and then when you want to deviate from that, you have an escape sequence that says change this to red, and then blah 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 blah, and changes to whatever, or changes to whatever. So you see escape sequences a lot in descriptions of formats.
It's operating systems and it have all the algorithms for coding all these different types of things. Or it's actually some software.
Not. I would say no, if I had to go one side or the other, but I would also say, well, where does an operating system end now and an application begin? Do you mean if I look at an image on my phone, the bit that reads JPEGs, I mean, okay, maybe that's a service that's built into the phone that something can call. Is that an operating system function? It's probably hard to say where the things.
Is it usually built into the machine or the coding?
Well, in the early days they weren't. I mean, in the early days someone had to go away and, write an image displaying program for each format. And, I mean, But I guess someone in Apple wrote a display JPEG type piece of code one day, so that no one else had to bother subsequently. Let me see if I'm still connected to the network. It does seem unlikely. Okay. Maybe Wikipedia is probably a better place to go. How are we for time? Okay. I so hope I'm right about the flags, because it's one of those stories that's like so convenient you wish it was true.
Like when you talk about the flag things.
I mean, guys on ships. I mean, this, look, this US Navy crewman signals using flag semaphore. Okay. So, yes, I'm right. So, this says numerals. So I think what you do is you say, I'm switching to numbers now, or else the next thing is a number. I don't know if you have to switch back to letters, maybe. Maybe you say, I'm switching from letters to numbers. So, as you can see from my hands here. So this says numerals. So then if I do, it's worse than the Macarena. Then if I do this, if I'm in numerals, if I've escaped to numerals, then this means 4, but otherwise it would mean D. And
all the Navy people on the boat, are we watching them then, or who's watching them?
you're two ships. Well, first of all, if you're a pilot, well, obviously the radio and everything, but this is probably mostly for, post-apocalypse.
Yeah.
But no, I mean, you can from ship to ship. Do you know what I mean?
Yeah.
If you're passing, it's better than shouting. And no, in the pre-radio days, I mean, it was the only show in town.
They all had to know it.
They all had to know it. And the captain would say signal, the lead ship would say signal a retreat, This is interesting here, isn't it? You do E 8 times to say error.
They look like an error anyway.
That's true.
I haven't seen it.
And
8 times to say error.
but isn't it interesting that all of this predates computing communications by hundreds of years, and you have things here, look, acknowledgement, correct, invitation to transmit. It's like a modem talking to whatever modems used to talk to.
Before that, would it be smoke signals and whatever? Would that be kind of
Well, do you know what now? I would love to see the syntax of smoke signals, because we might actually see in that even more, some other principles. I imagine, though, that smoke signals were more symbolic, so they were more like Japanese kanji, where you didn't make meaning by combining lots of small little things, that the whole meaning was communicated in the symbol. So do you know when the Power Rangers do, yeah, they're writing they're doing air kanji, okay, and those symbols, that entire symbol has a meaning.
emotions more than actual sentences.
It would be a word, it would be a meaning. So it would be like, you see, whichever Power Ranger you are.
Danger.
So if you're the well, they don't write colours actually. Like one is like the fire, one is the there's so many different classes of Power Ranger now as well. But if you look at you can tell I have kids. If you look at the animal Power Rangers, they're writing their animal sign in kanji. So in kanji, and the same in Chinese, the symbol means the whole thing.
Yeah.
So like that symbol means horse or dog or hot or chicken. Like whereas in English you make chicken, with a C and a H and an I and a K and an E and an N put together, or a sequence of sounds put together.
These are all just independent.
So I have no idea, but I suspect that smoke signals aren't constructed with bits of words, that the signal is the whole thing. But I would love to figure it out. So, so you can see in semaphore here, there's something. Oh yeah, look now. Numbers can be signaled by first signaling numerals. To change back to letters, simply signal J. Oh, where's that now? J?
Yeah, it did say.
Right. So, which is after 9. Yeah, okay. So, you know, if you're expecting a number and you get number J, well, okay, there's a sign there. Maybe you've gone back to letters.
But what if? Oh wait, so he does that, and then you have to do that again if he was to say.
Yeah. So I thought you'd have to do like number 7, number 4, number 7 to do 747, but no, you just say, okay, switch into numbers, do 747, and then
Switching to letters.
switch back to letters then with
Well,
J.
if you were doing if you switch back to letters and you wanted to do J, do you kind of go with that again?
You have to do J again, yeah.
Yeah.
Said he, as if he'd ever done this in his life.
I missed that one move there in the middle of what he was saying.
Yeah, you know.
But I was thinking, like, with that, how many combinations you would have, but that
Well, this is the question. Sorry, this is what I wanted to get, right? How many combinations are there? Right?
over 40,000, isn't it?
You
No, I put that in the
No, I mean just.
I put that in the
So your hands, like,
Okay.
16 arms.
so. No, so you can be like up here.
No way.
You want to be very accurate, though. You know, if you're far away, you want to have enough.
I guess that's why you've got flags. Do you know? So you've got like 1, 2, 3. Is there one below there? 4 and 5. So you can have 5 positions on one arm and 5 positions on another arm. So you've got 25
And he also had a flat
but that doesn't seem like enough.
No, but you have like arm
You got 26 letters.
Arm up 1, 2, 3, 4.
Well, you say 25, and he's got that one as well. Look, the third one there, error. Oh, that's
Oh, it is
there.
5 times 5. Where did I get 8?
I was thinking of that one as well.
I might have given it 7.
But hang on now, look, he's got 5, he's got 2 arms. You got 5 positions by 5 positions, no? 1,
No,
2,
cross.
3,
Cross
4,
See,
5.
O, he's crossed onto one. Same side.
because if you can cross, that's another.
Yeah, and W as well.
Oh, right, so you can do 2. Oh,
So you
Jesus.
technically you've actually got 125, don't you?
way off.
10 by 10, no 100.
That's true. If no, this is where now we get into like accuracy, right? Conceivably so in this scheme. Remember we said like 25 isn't enough. So something had to give, and that's how we got into putting 2 arms on the one side. So conceivably then, if your right arm could be in one of 10 positions, and your left arm could be in any one of 10 positions, well then you're up to 100 possibilities, aren't you? Now of course, this would be stupid, you know.
Yeah, well, like one thing.
But
If you count the letters in as well.
So-
J
so-
letters.
So take away another 20.
yeah, so theoretically at least you could have 100 options, but in the interests of readability,
You take away 10.
you're going to do away with many fewer. I mean, like, there's just too much scope for confusion otherwise. So you can see the 2 armed ones, right? I was going to say there's very few. I think the scope for confusing I with O, for example, seems very great to me. You know, but you could see how
The angle could be off
they've
by
kept
like
them kept them to quite a minimum. Again, though, no, I mean that's why you flags, so the positions are exaggerated. You know, I mean if these flags were a meter, I guess if you're in the Navy you're probably big and strong anyway. But if these flags were a meter, you know, long, I mean the positions would be more easy to see. Oh, the Japanese have something different. No, of course it's not a huge shock that the Japanese would have something different, since their writing system is so fundamentally different from English. They might have a completely different way of thinking about it. Yeah, that makes sense to me actually, but I'm not going to explain it to you right now. But Japanese, what time is it? Well, anyway, they're using katakana, which makes sense for Japanese. It would be inefficient. It would be very inefficient to do Japanese in Roman letters.
Is that the one they type with as well?
Hmm?
Is that the one they type with on their keyboards as well? Because it's
Yes, typically, yeah.
It's
Yeah,
fine.
yeah.
I think they're left to right. I think Arabic is right to left.
Arabic is right to left.
That's the only one, isn't it? The least one kind of ones.
Hebrew is right to left as well, I think.
Japanese and Chinese are left to right.
I'm not sure. I think the Japanese have a fondness of going from top to bottom as well.
yeah, top to bottom.
Top to bottom is very fond of that,
Left for books.
you know.
Oh, so
And
you'd actually used to
So
read
it's
the
like-
top of the page, which you
Yeah,
just read
you go from the back.
From
Oh.
our perspective.
Oh, you actually.
Yeah.
well, Japanese magazines start at the back and you go
Yeah.
this way,
Because you're reading that way.
which actually, if you're right-handed, probably makes more sense. But like we open our books here and turn them this way.
Probably just so used to it when you start.
Ah, yeah, you know.
Yes.
No, so that was interesting, and it would be fun to kind of set some of you down there and some of you up here and make you transmit a message, you know. But I had thought of that, but now that you've seen semaphore, it's hard to not unsemaphore it, really, you know. But I'm going to come up with something. Fear not. Oh, and I can even give you that today. Yeah, great. I have a plan.